So we welcome Professor Nergis Mavalvala all the way from MIT, and she came to sample our fine weather, fine whisky tonight, and also talk to you a bit about gravitational wave detection and work that she does. Nergis received a BA from Wellesley College in Boston, a PhD from MIT, worked as a postdoctoral fellow and research scientist at the California Institute of Technology before joining the physics faculty at MIT in 2002, was appointed associate department head of physics in 2015, and in 2017 some of you might have seen that Nergis was elected to the National Academy of Sciences. Nergis currently is the Marble Professor of Astrophysics at MIT. In 2010 was recipient of the MacArthur Genius Award as a physicist whose research focuses on detection of gravitational waves and quantum measurement science. She's a long-time member of the LIGO Scientific Collaboration and is part of the team that detected gravitational waves in 2016. In the quest for ever greater sensitivity in the LIGO detectors, Nergis has been conducting pioneering experiments on the generation and application of squeezed states of light, and on laser cooling and trapping of macroscopic objects to enable observation of quantum phenomenon in human scale systems. So let's welcome Nergis with us today.
So thank you, and wow, did I really do all those things? But good. So the one, thank you, Sue. The one very useful thing about that introduction is that I am actually going to touch on some of the science that's mentioned there. I'll talk about squeeze states of light. I'll talk a little bit about quantum measurement science as relates not just to gravitational wave detectors, but to other ideas in quantum information processing systems, etc. So the structure of my lectures is that I'm in your schedule for 3 hours, 2 today and 1 tomorrow, and I have 2 topics I want to cover. And if we get through them today, then tomorrow you'll be able to just take care of your hangovers. But if I don't, but by the end of today, we'll know if we need a little bit more time or not. And then the other thing is just interrupt me and ask me questions. So let me just get started by, in case you've been asleep this whole week, I like to think about gravitational waves in 2 ways. And actually, it turns out this is a very important way of thinking about it that got this field going. So when Einstein first proposed gravitational waves, people really got fixated on the sources. What makes gravitational waves? And that's on the left side of this slide for me. Now, it turns out that the luminosity of the gravitational wave scales as the Schwarzschild radius over the size of the object r squared, and also the speed of the matter in the object compared to the speed of light to the 6th power. And so very quickly people understood that to make appreciably luminous gravitational waves, you need a very compact object whose size is comparable to the size of its Schwarzschild radius, or to a black hole of equivalent mass, and also that you needed the material to be relativistic. And so those were so people started to look at ideas of compact objects in binary systems, for example, because you need lots of compact mass from this term, and you need rapid accelerations and in terms of orbits, explosions, collisions. So that was sort of what people were thinking about early on, right from the time of Einstein's introduction. People had not paid a lot of attention to what happens at a receiver. So here on the Earth, how do you make this measurement? Until the 1950s, and that was when, so it was already well known that they travel at the speed of light. It was also understood that I'm just bumping my own plug here, so I'll try and stay away. That they stretch and compress space-time self, and that the amount by which a space-time distance L changes is proportional to the amplitude of the wave. Now, it wasn't until the 60s and 70s that the amplitude of the wave got established to be around 10 to the minus 21, and that then tells us right away that these displacements are terribly small, but it turns out not as small as Einstein might have thought, because compact objects and binaries, because neutron stars and black holes, were not discovered in his lifetime. So we're going to concentrate on this talk on the right side, what happens at the receiver, and I'm only going to tell you about the parts of the receiver, the detector, that are going to be quantum noise limited. But the principles you have to know about and that you already have seen is, the first question I can ask you is, could you make a gravitational wave detector just with a mirror and a laser, a mirror, and a clock? And the answer is, in principle, yes, because the measurement actually, nothing in general relativity disallows us from simply shining a laser at a mirror and measuring the light travel time with a clock. Now, the reason we don't do that is for even large separations of lasers and mirrors, we don't have clocks that are precise enough to make a measurement of the change in travel time of the laser beam as the gravitational wave passes through the laser mirror space. And that's why we use an interferometer. So the reason is really just that the interferometer is a relative measurement. Instead of using an absolute clock, what you do is you use one arm as a reference to compare the wavelength of the light in the other arm. And so there's two things you need to do to make a good gravitational wave detector. And in simplest terms, you need to make mirrors that are very, very still. And that means you actually have to do a lot of vibration isolation. And you also have to control the thermal fluctuations. So those are the two things you do to the mirrors. And then once you have these mirrors that are still enough to respond only to the passing gravitational wave, that does you no good unless you have the ability to measure very small motions. And that's where the laser light comes in. The laser light is our meter stick for measuring the positions of mirrors. And it turns out that even with the finest of laser light that we know how to make, it's typically not good enough. You have to do a little bit better. So my talks, both of them in the end, ultimately are going to be about this piece of it, which is how do you do high precision optical measurement, and that involves manipulating the quantum states of light. Okay, so that's really what this next 2 or 3 hours is about. Now, pictorially, what this is I just want to make a little disclaimer. My talk will be a little bit LIGO-centric, just because that's the instruments I know the best. But wherever I can, I'll tell you a little bit about how some ideas that I put out are used elsewhere as well. So what you need to know about LIGO are the same two things that I told you on my previous slide. These are these L-shaped interferometers. Now, you must have good vibration isolation in systems like these. You must have mirrors that are suspended as pendulums that are part of the vibration isolation system. And once you do that, you must have a good laser. Okay, so again, we just come back to those three things: still mirrors and good lasers. I also want to just point out to everybody, and this will be interesting for us in this evening's panel, that LIGO was primarily, for its US components, was funded by the US National Science Foundation. I never give a talk without pointing that out, because I think this has been an incredible partnership. So here's what LIGO's facilities were designed for. And this is an amazing thing to contemplate, because these ideas were first put in place in the early 1970s, and then refined in the 1980s and late 1980s. So this has been a very long thing. But here's an interesting thing. You've all seen plots like this now of sensitivity, frequency on the horizontal axis, and spectral density of strain on the vertical axis. If you don't like thinking of gravitational wave strain, simply take this vertical axis and multiply it by 4,000 meters, and that will give you displacement noises. And for most people who work in labs, displacement noises are more intuitive, so just scale this up by 4,000 for LIGO. So what you see here is in the red is the actual target sensitivity that the first phase of LIGO was designed for, and this red curve was in some rudimentary form already known and proposed by 1972, primarily by Ray Weiss and others. Now what you see, the blue curve is very interesting, because what the blue curve is what the LIGO facilities were built to be. So let's take a look at what limits the facility and see what the gap is. So the facility is limited by two things. At higher frequencies, above about 10 hertz, it's actually limited by residual gas. And what does that mean? This is how good is your vacuum system, and how many residual molecules do you have floating around in the vacuum system. And why is that a limit? That's a limit for two reasons. The primary reason is that when you have gas molecules, even very few, floating around, when they cut through your optical beam, they change the refractive index. Change of refractive index of light looks like path length change. Path length change looks like a gravitational wave, and so that's no good. So that's this part here. And then on the vertical axis here, we have what's called gravity gradient noise, more accurately known as Newtonian noise. And that is to do with local fluctuations in G. So we think about the gravitational force on the mirrors as something that's constant. Actually, it turns out it's fluctuating. It can fluctuate due to to different mass densities in the neighborhood of the test masses. So it could be a cloud floating overhead, or it could be some density perturbation like a seismic wave under the test mass as well. And so that's what the two limits are, and you can see that there's a big gap of actually many orders of magnitude, because each of these divisions is 2 orders of magnitude. So there's about 5 orders of magnitude to go between what LIGO was initially made to be and what can be in the facilities. And we're going to come back to this later today when we talk about future detectors. Okay. So this has been the history of LIGO in the past, present, and future. Starting with the green curve, that's what LIGO operated at in 2010, and that was the last of LIGO's scientific observing runs in its first phase, which was called initial LIGO, which ran from about 2000 to 2010. Then we ripped up the old detectors and started making our way to the advanced LIGO detector, and the target sensitivity for it is given by the blue curve here. But shortly after the commissioning of this advanced detector was completed, we did our first observing run, and you all know what happened there, and that's these red curves here, and the 2 red curves are for the Washington and Louisiana observatories. And then finally, I've also put on this plot this cyan curve, which I simply call upgrade. It's sort of a catch-all. Now, this is going to be an important plot for you to pay attention to, because it kind of motivates everything that I'm going to talk about next, and that's really to do with how do we make our way from where we are now with observing run 1 and 2 being close to completed to the advanced LIGO design sensitivity and beyond. Okay, so that's really what we're going to try to talk about. Now, to actually go beyond advanced LIGO, we need to know what limits advanced LIGO itself. And so here's a little a schematic of the most dominant noise sources. Now, there's all kinds of noise sources that are written down here. I only want to draw your attention to 3. Okay, so the first one to notice is the purple curve, which is called quantum noise, right there. This purple, and look at it, limits the sensitivity of advanced LIGO pretty much across the entire band in some form or another. And I'll say a lot more about that, because the whole rest of today's, of this morning's talk, and maybe even the afternoon talk for a bit, is going to be about how do we do better than this purple curve. And then you see this red curve here, which is called the coating Brownian noise, and that's actually to do with the thermal noise of the optical coatings on the mirrors. I want to ask, have people talked in the past week and a half about the thermal noises and Brownian noise of coatings? Good, so you're all experts on that. So I won't say a lot more about it than to say it's here, and it's a pain in the butt. And in fact, the one thing you should take away from that, even though I won't talk much about it, and I'll spend a lot of time talking about how to do better with the quantum noise, you must remember that we won't really gain much if we improve the quantum noise by a lot and don't get this coating thermal noise to be better. So this has got to be a tandem effort. And then the third interesting plot to see over here is, as you notice, compared to initial LIGO, that was limited by, if you go back to this plot, you see initial LIGO is limited by seismic noise all the way almost, from low frequencies out to about 60 or 70 hertz. If you look at advanced LIGO, seismic noise, which is the brown curve, really doesn't get in the way at all. It's completely dominated by the green curve, which is that Newtonian noise that I talked about. Okay, so you can see that those are going to be the 3 things to deal with: Newtonian noise, coating thermal noise, and quantum noise. Okay, and so if you want to do better than advanced LIGO, you have to think a little bit about what to do about those 3 things. Okay, so when we look at going beyond advanced LIGO, those are the 3 things that we have to deal with. So for Newtonian noise, again, I won't say much other than that there are ideas out there and some very pretty experiments and data that show that you can actually do a little bit better, and by a little bit I mean factors of 2. Now in our field, you know, factors of 2 are very attractive, right? Because factors of 2 in sensitivity means factors of 2 cubed in event rate. So that's pretty nice. So by outfitting your test masses with seismic arrays, measuring all the variations in local G or seismicity, reconstructing how that affects the test mass and regressing it out. And that can win you a factor of 2 or 3 perhaps. Similarly, putting your test masses deeper underground can also help, because it turns out that your susceptibility to mass density fluctuations, the mass density fluctuations are smaller as you go underground. So you could do that, and that's part of why you might have heard about the Japanese detector Kagra that's actually in an underground mine. Okay? Now, thermal noise, there's 2 knobs you can turn. You can cool cryogenically. That's one thing you can certainly do. Pretty difficult to do. Or you can use lower dissipation materials, and that's really been the way that advanced LIGO has dealt with thermal noise. There is no cryogenic cooling planned for advanced LIGO. It's been the thermal noise compared to initial LIGO has been improved by using lower dissipation materials. And then finally, there's quantum noise, and there are 2 sort of ideas out there for quantum noise reduction, and they're actually part of 2 sides of the same coin. And one is to use squeeze states of light, and the other is to use some other back action evasion techniques. And I'm going to talk a lot about that. Now, there's something that I should put out here that is inevitable as we think about going beyond sort of incremental factors of 2 and 3 compared to advanced LIGO sensitivity, which is that soon we're going to be faced with having longer detectors. I think that's inevitable, and we should put it out on the table, because what choices we make for these technology improvements is informed by whether you can make your detector longer or not. All right, so that's what we're going to do. Now, there are many options to consider, and all kinds of options have been considered, from 10 to 40 kilometer long arms, underground caverns, cooled mirrors, using different materials for mirrors, having different detectors for low frequency gravitational wave detection versus high frequency gravitational wave detectors. It turns out no matter how you cobble together these different ideas that are shown in all these different colorful curves, with advanced LIGO being way up there, and then all the different ways in which you might be able to configure an instrument, it turns out there's one technology that shows up again and again and again. There's no instrument that's being considered anymore that doesn't involve squeeze states of light. And the reason is that the technology is quite mature, and we think it can really help. So I'm going to now spend the rest of my time this morning just telling you about squeeze states and how we make them, what can they do for us. All right? Okay, so to get beyond quantum noise, to do quantum engineering, we first have to understand the quantum noise itself. And that requires us to take a little journey into the world of quantum optics. How many of you have ever had a class or seen quantum optics in some academic setting? Okay, a few, good, but not many. So I'll give you a little primer, and for the few that have, I think you can just have a little power nap, and for the many who haven't, this will get you started down the road. But before I do that, let me just tell you what are we going to talk about? What piece of quantum optics, am I going to have to talk about? So this again is the initial LIGO sensitivity, and then we turn on we come up with the design for advanced LIGO, which is the black curve, and one of the very big differences between initial and advanced LIGO is that we increase the laser power. And so what we've done is, so in initial LIGO, the laser power was 10 watts. And in advanced LIGO, the input power, the power that you introduce into the instrument is 200 watts. Okay. Now, just as in case there are theorists in the room, just to put a scale on this laser pointer, anybody want to guess what its power is?
Microwatts?
No, it turns out a little bit. Yes, many microwatts. Yeah. So it's typically a few milliwatts. So 1 to 5 milliwatts. Okay. So when you talk about a 200 watt laser that shines continuously, it's got a lot of energy density in there, and not something you want to ever stick your eye into, for example. But that's what was done. Now, what happens as a consequence of this increase in power is that this part of the initial LIGO curve right here above about 150 hertz was limited by the quantization of the light, right? It's limited by shot noise. Did people talk about that already?
No.
Shot noise? No shot noise yet. All right, very good. So shot noise comes about from the fact that light is quantized, we know that, and it turns out that a laser is a light source, and when you think about different kinds of light sources, you can think about a light bulb, and that you would call a thermal light source, which simply means that it's basically got no coherent photons. The atoms on the tungsten that are emitting photo emitting are uncorrelated to each other. Now it turns out that the distribution of photons coming from a good laser is Poisson distributed. So they have phase coherence, but they're uncorrelated to each other in terms of say an emission time. Okay, so because the laser the photons are Poisson distributed, that means that if you make a measurement that involves n photons, then from the Poisson distribution you will have an uncertainty of square root of n. Okay? So that's really all it takes. So now my signal that's coming out of my interferometer or any optical device I use scales with the number of photons, whereas the noise scales as the square root of the number of photons. So your signal to noise ratio goes as the square root of the number of photons. So if I get 100 times more photons into my measurement, I should have a signal to noise improvement of 10. And that's really what happened right here. So that was what we did. We actually got a more powerful laser, and this shot noise goes down. Now comes another sort of real bugaboo of quantum measurement, which is that if you were making a classical measurement, you can think about making a measurement with no price to pay. You just make a better measurement, right? So classically you'll say, okay, I've increased the number of photons, I've made a stronger measurement. Now in the quantum measurement world, that simply can't be, because in the quantum measurement world you have measurement back action. So the whole idea, the simplest one that you've all learned about in your quantum mechanics class is a particle, quantum particle. If you know if you measure its position very, very precisely, you can't know its momentum, and therefore you can't know where it will be in the next instance, right? Now the equivalent of that here is that I've made a position measurement on my mirror very well, because I've put more laser power in. But now, and this takes a little digression into classical optics again. We all know, and we know this from time of Maxwell, this has nothing to do with quantum mechanics, we know that light carries momentum. And so now we have more photons, and those photons actually impart momentum to the mirrors and therefore move them. And that's the classic conundrum of quantum measurement. The act of making the measurement disturbs the measurement. I put in more laser power, so I get a better measurement on the position of the mirror, but those larger number of photons give greater kicks to my mirror, and that's a larger back action. So if you've always heard about these ideas of quantum back action, but you still always have to uphold Heisenberg. So I'm going to talk a little bit about that. Now it turns out that there is a metric that's used. This dashed line that I just introduced is called the standard quantum limit in our field, in the gravitational wave detection field. Now it's a terrible, terrible name, because it is neither standard nor is it really a limit. But let me just tell you what it is. I like to think of it as a sort of a benchmark. It asks a very fundamental question, which is a lovely question to ask, and which we'll touch on quite a bit in the afternoon talk. And that is, if I take a particle and I try to measure its position using light, how well can I do? And you know now that you can't do infinitely well, right? Because I'm tempted to use lots of light, so I make a more precise measurement because of this shot noise limit. But that more light, because of the same quantum fluctuations, gives fluctuating kicks to the particle I'm trying to measure. And this is the balance of those two. That's why it's called the standard quantum limit. And I'll show you that we can get around that in the afternoon talk. All right? Okay, so that's the problem we're facing in advanced LIGO. That's where all of our headaches come from when we think about quantum noise. And so to understand where does the quantum noise come from, we do a little journey into the quantum mechanics of light. So all of you have seen an equation like this for a classical electromagnetic field. And in this case, I've been a little bit lazy. I've kind of swept all of the spatial dependence into the E1, E2 vector. And there's the time dependence in terms of cosines and sines, right? This is just your standard traveling wave in electromagnetic wave with two polarizations, E1, E2. Now, it turns out if you want to quantize this electromagnetic field, you can. What you have to do is you have to take every single mode of an electromagnetic field and you have to treat it as a harmonic oscillator. And what this means, and in this case it would be a quantum harmonic oscillator, and what that means is that each of these terms here, of each polarization, you can now write as a mode with a raising and lowering operator. So you can think of it as an oscillator oscillating at frequency omega, but it now has, it can be represented in terms of raising and lowering operators. And when you do that, the quantized field looks like this. You replace these E1 and E2 amplitudes with quantum amplitudes, turns out to be quantum operators. We call them X1 and X2, but they're actually very easily defined in terms of the raising and lowering operators of the photon state. So what's being raised or lowered here? Photon number. If I take a photon number state with one photon and I apply the lowering operator to it, I get a photon number state with 0 photons. It's the same ideas as you've done with the quantum harmonic oscillator, except this happens to be an electromagnetic oscillator, and then the actual electromagnetic field would be a sum of all possible such oscillating modes, okay? And you will also notice that X1 and X2 remind you of something else that you've also seen in your introductory quantum mechanics classes. They remind you of position and momentum of the quantum harmonic oscillator. And that's because these play the same role in the quantized electromagnetic field as position and momentum do for a particle. What that means is they have to follow the same commutation relations. That means you have to then follow all of the rules of a quantum harmonic oscillator. And that also means one other thing that is inherently quantum mechanical, and that is quantum uncertainty. And so these are the commutation rules that these operators follow, and I won't go into the details, but if you go back and look up, if you've forgotten, as we often do, because it's been, for me, many years, and for you, a few years since you did the quantum harmonic oscillator, you'll notice that this is the same commutation rules for position momentum, and also, therefore, the same Heisenberg uncertainty rules as well. So now we're armed with two things. In classical fields, you would write these as two quadratures. These are always known as quadratures because cosine is 90 degrees offset from a sine. And so X1 and X2 are known as quadrature amplitudes. We'll talk about them all the time. They're not exactly amplitude and phase because they're actually if you wanted to write this in terms of amplitude and phase of the light, they would be some linear combination of X1 and X2. So, but the hermiticity is X1 and X2. So we'll talk about quadratures, okay? And so now if you ask about this more, so that's the formal stuff. I've swept through away all of the details about how you construct a coherent state, but I want to tell you pictorially how to think about it. So if you had an electromagnetic field, a completely classical field, you have your standard phasor where you have the real and imaginary axes, and you can write the amplitude and phase of the field simply by the length of this vector and the angle it makes to the real axis, right? Now in quantum mechanics you can't do that anymore. In fact, you can't, because you can't know those two things with infinite precision. And what that means right away is that if you have a coherent state, which is what the laser light is, it inherently has a quantum uncertainty circle. And it has a circle because, just like with your quantum oscillator, it's a minimum uncertainty state. It's a Gaussian state. Okay? So it has equal uncertainty along the two quadratures. Remember now, look, E1 and E2 were replaced by X1, X2. And it has this uncertainty. And so if you wanted to describe this quantum light field, it's basically the same as your classical. It's rotating at omega, at the frequency of light. But you can't know what the tip of the phasor is. And what that now allows us to do is to introduce new ideas, new, they've been around forever, but for you maybe new, is to generate a squeeze state from this idea. So a squeeze state is the same. Your two complementary observables are X1 and X2. But what you must do is you always have to satisfy this Heisenberg uncertainty principle for what the uncertainty in each quadrature is, which means the product has to satisfy the uncertainty principle, but you're always able to make the noise smaller for one of those two observables as long as you ensure that the noise in the other quadrature gets larger. And by a very fixed relationship, which is this. You can arrange a squeeze state like this one, where along the x1 axis you've shrunk the noise uncertainty, so you've made the ball, the short part of the ellipse smaller than the radius of the uncertainty ball, as long as you make the long part of the ellipse longer by the same amount. And that satisfies your uncertainty relation. Okay? So that's the trick we're going to play again and again, but now I'm going to tell you, so that all looks easy. It's easy to say in words. What does it mean for an interferometer and how can we do it? All right? So, in an interferometer, what role does this play? And this brings me to, again, another interesting difference between classical light and quantum light, and classical beam splitters and quantum beam splitters. So let me ask you the classical question first. Imagine I make an interferometer like this, which it's perfect. So it has a perfect beam splitter, 50% of the light goes up this way, the other half this way, perfect mirrors, the light is reflected back. And now we arrange these two path lengths so that we have perfect destructive interference at this output port here. First question, if you have perfect destructive interference, that means it's dark, where does the light go? Goes back to the laser, energy conservation, right? So we all agree with that. Now, imagine that you had noise on the laser. Imagine that your laser had fluctuations on it, just because the laser water cooling rattles the laser cavity or something else. Where does that noise go? It's not a trick question. Your intuition should be with you at this point. This is classical.
It goes to sensor.
It actually goes back to the laser, because the noise, the classical noise on the laser and the coherent field, the noise doesn't know I'm noise, I should do something different, right? It originates with the laser beam field and goes back to the laser. Yet, if you made a measurement at this output, I told you would actually measure noise, shot noise, right? So the first thing I want to tell you is the shot noise does not come from noise on the laser. So where does it come from? Now it comes to the last of the sort of quantum optical things you have to think about. This interferometer is an open quantum system. And what's the biggest difference between a classical and a quantum field? Does anyone tell me? If you had to name one property of a quantum field that's both counterintuitive and doesn't even exist in the classical world, what would it be?
Particle numbers not necessarily.
I'm sorry?
Particle number can change.
The particle number can change, but I would argue with you that's true, but I can always introduce noise in the laser that would also cause amplitude fluctuations. So the particle number would change. No, it turns out to be something much, much more fundamental. It's the 0 point energy. The quantum vacuum fluctuations. Okay? And so for example, when you modeled, last week at some point you modeled some interferometers with Andreas, for example. The classical fields that you modeled, if you wrote the code for a classical field, it would be missing one very important thing. That classical field would not ever be able to introduce quantum fluctuations into the interferometer. So what are the quantum fluctuations? The quantum fluctuations are basically, this is an open port, because this port is blocked by the laser beam, this port is blocked by the perfectly reflecting mirror, as is this. Here you have an open port. Now what can happen there is the electromagnetic vacuum state can enter. Now notice this is a quantum state, it's x1 and x2, but it's a little bit different than the state I showed, the coherent state that I showed you. What's the difference? There's no length to the stick. It's just an uncertainty ball centered around 0. What does that say? It simply says that I have 0 photons in the field, but I still have 0 point energy. And that we know is, all field theories give us that. So that's okay, we can live with that. Now what this field does is, by the symmetry of the beam splitter, for the same reason that the laser light always goes back to the laser, this field, whatever it is that goes in here, reflects off these mirrors and comes back at this output here. Okay, right here. Now if a gravitational wave came by or any other disturbance and the mirrors move relative to each other, a little bit of the laser light itself also exits this port, and that laser light superposes on that vacuum state. And now you see that you have uncertainty because of the vacuum state. And it turns out that is what the shot noise comes from. The shot noise that we talk about in these instruments comes from the coherent signal field, which was this little red phaser here, superposing on the vacuum fluctuations.
So, one thing that confuses me about this image is, are these quantum fluctuations really, like, is it just to help pictorially, or do quantum fluctuations really propagate down the beam tubes and bounce back, or is it that they're just superimposing on the returning laser near the dartboard?
Both descriptions would work, but I will show you an experiment that unequivocally will prove to you that the quantum fluctuations originate here. Now I'll do that in the next 5 minutes. Okay, an experiment. So remember, I'm an experimentalist, so when I could write a number of equations here for you that should convince you, but that doesn't mean anything. It's what nature does that matters, right? So I'll show you. So that's the shot noise comes from that. It turns out that the radiation pressure noise, that back action, the kicks of the mirrors, comes from the same thing. It's the same vacuum fluctuations. So let me show you that. So it's these same vacuum fluctuations that superpose with this very intense field at these mirrors and give the mirror kicks, okay? And so that's the origin of the quantum noise. The origin of the quantum noise is the electromagnetic vacuum state that enters the open port of the interferometer, okay? Repeat after me, because this is something, if you haven't thought about, the first time I saw this, I was like, this is nuts. But then we did the experiments to show that maybe it wasn't. Okay, now comes this idea. Yeah?
But I don't know. I understood it so far that, right, like we were creating in a Poisson process light.
Yeah.
So there will be a fluctuation of how many photons come out.
Yeah.
But you say that has nothing to do with what we actually see as shot noise in the end, because that just goes back to the laser.
Right, but I'll tell you where the number of photons does matter. So the number of photons does matter. So you would say to me, well, how do I know then that I should get sensitivity at this measurement that goes as square root of the number of photons? That actually turns out to come from the size of the signal phasor. So the vacuum state and how much of the vacuum state you superpose depends on this size of this phasor. So that's really where that enters. How does a number of photons enter if it's a Poisson process all going back to the laser? The number of photons enters. So another way to think about the same thing is that if I have a vacuum state out here, if I really succeed in making a no signal come out, so really 0 photons, I will never be able to measure it. So you can't measure a vacuum state without superposing it on some number state. That's another way to say the same thing.
It's two stochastic processes, right? It's one from the laser itself and then one from the, vacuum.
Right.
Okay.
That's right. Good. All right. So, and by the way, these ideas were very, very controversial in the late 1970s, and were actually ironed out eventually by Carl Caves, who was at the time a student of Kip Thorne's at Caltech, who first gave us this idea of looking at this open quantum system. And so, if you were puzzled by it, confused by it, outraged by it, so were many other people when they first heard about it, okay? All right, so now let's talk about what can we do. So here's your vacuum state. Now suppose that I could squeeze this vacuum state. So I make a state like this. Now you're used to that. It's a state where one quadrature has greater noise than vacuum and one has less noise. Now that squeeze vacuum state propagates into the interferometer the same way as the vacuum state would, and it comes out here at the measurement port. And now look, I've carefully arranged this so that the narrowest part of the squeezed ellipse is along my signal. So inherently, I would make a more precise measurement than if I just had the vacuum state. Now it comes at a tremendous cost, and you have to be very careful with that, because if my signal phasor is at all misaligned, so have some projection along the long axis of the ellipse, then my measurement is going to be destroyed, because now I'm going to sample greater noise. So this is not a violation of Heisenberg, but it's a very, I would say, it's a very handy manipulation, right? We're able to reallocate noise, so we send it out of our measurement and into something we don't measure. Okay? So that's the process. That's what we do. So now I'm going to argue that if I put in a squeezed vacuum state like this into my interferometer, I should make an improved measurement. So let's see, this is the theory, and then I'll show you the experiments. So here is the advanced LIGO design sensitivity, is the blue curve. And now look at this, I have a red curve where I'm inserting what we call 6 dB, or factor of 2 in signal to noise, of squeezing. And look what happens. The red curve is happily below the blue curve. We make some improvement. And then we think this is great, but look what happens as we plot along here. There's a certain frequency at which the red curve exceeds the blue curve. Anybody want to say what's going on there? Take a guess, or even know it and tell me. Why is it that I just spent all this time telling you my squeeze state should make it better, and indeed at these frequencies it makes it better, and then at low frequencies it makes it worse? What's going on?
The noise is becoming dominated by the other quadrature.
Exactly. So at these frequencies, at these high frequencies here, imagine that I'm making a phase measurement. So the optimum squeezing should be, say, a horizontal squeezing ellipse. Now it turns out that because of the way that the interferometer is configured and the frequency response, the other quadrature, the amplitude quadrature, starts to dominate at these frequencies where the mirror kicks are important. And so there, the optimum quadrature would be something that looks like this. And actually, as you go through this frequency response of the interferometer, the optimum quadrature right around here would be something in between. So this is a sort of I made you very happy first to tell you squeeze states makes everything better, and now I should make you sad. It doesn't make everything better. It comes at a cost. Now it turns out if you could make a squeeze state where the quadrature rotation of the ellipse was dependent on frequency, you could make a curve like this, and you would get broadband improvement. So I'm going to tell you about all of these things. We're going to make a squeeze state that looks like the red curve. I'm going to show you how we make a squeeze state that looks like the black curve, and how we can get broad improvement. Okay? All right. So squeeze state generation. How do you make a squeeze state? So first you have to wrap your head around how do you make a squeeze state at all. And then you have to wrap your head around how do you make a squeezed vacuum state. Okay? So let's wrap our heads around these things. So how to squeeze a photon state? So what do you need to do, right? We already saw this. What you need to do is you need to take this kind of quadrature representation. And what you want to do is you want to take the circle in quadrature space and turn it into this ellipse, where the ellipse grows longer along the semi-major axis by some quantity e to the 2r, and therefore it must get smaller by e to the minus 2r in the orthogonal quadrature. And that ellipse is free to rotate relative to these axes by this angle theta. That describes everything we want to know about the squeeze state. But how do you do it? So there's one word that would answer that question, and we'll talk about how that happens, and that is correlations. So what you need to do is you need to correlate these quadratures. So if you had two uncorrelated quantities, you would write them simply as, you would write the total noise as simply the quadrature sum of the noise in each quantity, right? So if you had delta x, delta y, well, the quadrature sum would be delta x squared plus delta y squared. Square root of that would be the total noise in this joint measurement you make. Now, if you could make a correlation where the cross term has a sign that you can control, you can immediately see that your noise can get larger or smaller than the minimum. And that's the game we play. So what we have to do is we have to create correlations between quadratures. So let me give you a very simple-minded idea, and then I'll do the more complex one. Imagine you had a material, some optical material, where the index of refraction of that material depended on the field, the electric field in the material. And we have many such materials. Kerr materials are like that. Pockels materials are like that. So now as the light passes through a material like that, you get some dependence of the index on the intensity of the light. Now, refractive index means phase shift. So as the light passes through the material, it acquires a phase shift that's not just proportional to the distance traveled in the material, but also on the intensity or amplitude of the field. And now what have you done? You have correlated phase to intensity or phase to amplitude. So that's a simple-minded way to think about it, right? Where you have phase quadrature and amplitude quadrature, and by passing it through a nonlinear material like this, you correlate them. So that's the simple-minded idea, and it turns out that this simple-minded idea is the basis of more or less what we do, but I'll give you sort of the more sort of formal picture about it in a moment. So what's our squeezing wish list if you want to make squeezing for a gravitational wave detector? Well, you want large levels of squeezing, so I like to say 10 dB. 10 dB would be a signal to noise ratio improvement of about a factor of 3. And as we go through the squeezing discussion, you'll see that is not easy. Okay, so 10 dB, so factor of 3. What we'd like is squeezing in the audio frequency band. Remember, gravitational wave detectors have their best sensitivity between 10 hertz and 10 kilohertz, so that's why we need to generate these squeeze states. We need long-term stable sources of squeezing. And then we also have one other really important requirement. Turns out this is a requirement for any technology you introduce in a gravitational wave detector, which is you can't add noise at other frequencies that your squeezer may not care about, but of course the gravitational wave band cares about. So we call it the do no harm rule. And none of these, by the way, are easy, but I'll walk you through what it takes. So here's how you can generate a squeezed light source. You can use a nonlinear optical interaction. And the nonlinear optical interaction is given by this Hamiltonian here. And I'm going to spend a couple of minutes on this Hamiltonian because as we make our way through to the afternoon talk, where we'll talk about optomechanics, you're going to see remarkably that this Hamiltonian appears in a completely different system as well. So what is this Hamiltonian? It basically has two modes. So A and B are modes. And in this case, they happen to be modes of two optical fields. And these two optical fields are related to each other by one field having twice the energy or half the wavelength of the other. Okay? So we have two fields A and B, and it turns out just for exactness and to sort of wrap your head around, I'm even going to give them real colors. But real colors meaning colors that happen in our experiment. So imagine there's a field B, so that's a green photon, and then there's a field A, which are infrared photons that are of half the energy or twice the wavelength. Okay. Now, if you have a black box that has this kind of Hamiltonian, kappa is just a coupling coefficient. It's a nonlinear coupling coefficient. That's a material property. This Hamiltonian tells you two different things. Here is an A dagger A. That's the number state of the A field. Remember, now we're getting to, people know about number states or Fock states from quantum harmonic oscillator. Here's your quantum harmonic oscillator, just happens to be a light field. So that's your number state. And what this is saying is, look at these are creation operators. So what this is saying is that you start with one B photon and you create two A photons, which is this process. You take a green photon and you split it into two reds. Energy is conserved, and by some details that I won't go into, so is momentum. And as a result, these two red photons were born from a single green, and their properties are correlated. Okay, and that correlation is, and the efficiency of the process and the degree of correlation is all hidden in that quantity kappa. That process is called parametric oscillation. You can go the other direction and you can do second harmonic generation. What that simply says is I can take two red photons and create a green photon. That's another process that's completely allowed by this Hamiltonian and is contained in this term. Notice here, what happens is I have a creation operator for a B and an annihilation for the A. So two A's died to make one B. Right? And that's how you read all of these Hamiltonians. If you've never seen these kinds of nonlinear dynamics Hamiltonians, they almost always look like this. You have some operators that are associated with a field or a mode of oscillation or something else, and they're always showing how they create and destroy modes that they're coupling to. And then finally, there's another process here that's called a parametric amplification or a four-way mixing mode that I won't go into. But the thing you must know, and this is now very intuitive from just looking at these pictures, is that the output photon quadratures are correlated because they are born from the same parent processes in a single nonlinear interaction. Okay, and that's how correlations come about. And so, you know, I don't know if you learned so much from this, so I won't go into the details of this. So here is now what a typical squeezing apparatus is going to look like. What you want at the end of this process is 2 red photons, because our laser, the laser that we pump our interferometers with happens to be, and when I say red, I mean infrared. Our wavelengths are 1064 nanometers. Okay, so that's written down here. So the wavelength at which LIGO operates is 1064 nanometers. So the very first thing is we take a laser, and this laser happens to be at 1064 nanometers, and we pass it through this second harmonic generation process. So I take a whole bunch of red photons, and with about 50% efficiency, or a little bit better, I make some green photons. Then what I do is I take those green photons and I push them into the second part of the process, which is the optical parametric oscillations. Remember, the second harmonic generation was to take 2 reds and turn it into a green. Now this gives me greens that are intrinsically phase locked to the master laser. Okay, so that's the only reason. I could have started with green photons here with a separate laser, but then I would have to phase lock these lasers. So you can go either way. So the whole purpose of this is simply to give me green photons that are phase coherent with the laser beam that feeds the interferometer. Those green photons go into this optical parametric oscillation process, and remember that was the converse. It takes 1 green and makes 2 reds, 2 correlated reds. So that's what comes out over here. And then I can make that measure what happens there on something called the balanced homodyne detector, which simply takes this laser field here, this other field coming out of the OPO here, and measures what they are. Now what's going on in this balanced homodyne detector? So imagine that I have some state here. It can be a light field or a vacuum field. This light beam here simply is the local oscillator that allows me to make the measurement. Remember I told you I cannot measure a vacuum state without some real photons? So that's what that measurement does. So if I have squeezed a vacuum state here, this dashed line is the vacuum state. I have no way of knowing what it is until I beat it on this beam splitter with the coherent field. So that's what it is.
Sorry, I think I missed this. So how do you go from, how do you get to just the vacuum state?
That's a very good question. I was going to come to that, but let me just do it right here because it's good. So how do you come to a vacuum state? So think about this pictorially first. So pictorially what I have is, I have a state that looks like this. And I told you that this was a coherent state, right? So this is my uncertainty ellipse and so on. So imagine for a moment that I take my laser beam and I put an attenuator in front of it. What happens? You attenuate it. So on this phase, picture what happens?
Stick gets shorter.
Stick gets shorter, exactly. Keep attenuating it till you have nothing. What do you get? Vacuum state. And that's what we literally do in our experiment. We set up the whole experiment with a real coherent field, with laser beams, we align, we lock, all of that, and then you simply block it. I can put my hand there. And it turns out that in quantum optics, your hand is a source of vacuum photons. So that's what we do. So in terms of the experiment, it's really just dialing down your laser field with a beam block, if you will. And of course, you have to do a lot of other things before you can do that to get it all working, but that's what we do. And so that's how we make the measurements on the balanced homodyne. And then what happens is, if you now want to inject the squeezing into an interferometer, this is how you would do it. Now you remove that balance. Remember, here was the balanced homodyne that was making the measurement of this squeeze field. We remove the balanced homodyne and instead send this field off into the output port of the interferometer through a process called a Faraday rotator, which is a detail, simply is a way of taking this beam and sending it this way. Okay? And then that Faraday rotator is also the place where the gravitational wave signal is measured. This ASPD simply means that's where the gravitational wave signal is. And if you did it correctly, you would have an output that looks like this, where the red curve is what you have without your squeeze state, and the blue curve is what you have when you put your squeeze state in, and the noise is lower. That's what you should have. So let's ask if this really happens. Oh, there's one other thing I want to say. Now imagine for a moment, so this would give you this frequency independent squeezing, which you remember those plots where I would make it better at some frequencies but worse at others? Now, if you wanted to do the broadband squeezing, then right here where you input the squeeze field into the interferometer, you have to introduce a few optical cavities, 1 or 2 or 3, but you can do it with 1. I just put 2 there for as a sort of an idea. But what happens is that when the squeeze field reflects off this optical cavity, its squeeze ellipse is rotated in a frequency-dependent way. And I'll show you some data from that in a moment. And so those are the pieces of the squeezing apparatus. And you can see here.
Excuse me?
Yeah?
So you mean essentially when the gravitational wave runs through, then it will rotate at the same time?
No, this is done in a steady state. It simply says that at a kilohertz, I have a squeeze ellipse that looks like this. And at 10 hertz, I have a squeeze ellipse that looks like this, and somewhere around 100 hertz, it makes the rotation. So this is done in a steady state. It's not in some time evolving way. This is continuously being done, and so when you make a measurement of the spectrum of the noise, it's lower at all frequencies, at all times.
Okay, so it's not a response to the rotation.
No, not at all. It's basically doing its own thing just to shape the response of the noise.
So isn't there several of these cavities like after each other to get every frequency working?
No. So it turns out that in principle you can do it with one single cavity. And I'll say a little bit about that in a moment. I'll show you data actually. So.
One more question. I think it's
Yeah.
a weird question because I just look at it. Could you go back to the previous plot? Why do we have to take the laser from the? I know we have to kind of get it coherent somehow, but I don't understand why we need the original laser essentially. Because I feel like down there we do the.
You don't. I already said, and I'll say it again. If you could bypass this whole piece of SHE and this laser by taking a green laser, which by the way, most good green lasers are nothing but a second harmonic generation process. Anyway, but say you start off with a box, you bought it from a company, it's a green laser box. You could get the same thing by taking that green laser and phase locking it with very high fidelity or high bandwidth to the pump laser. And here's the reason why. Remember that I already alluded to this. What we are doing is we are describing this quantum field as the sum of all possible modes. But really your interferometer is not all possible modes. Your interferometer resonates in one particular mode, which is this 1064 nanometer mode with both the frequency and spatial and temporal properties that it has, not all possible lasers. And so this is really just a way of saying, of all possible squeezed vacua, I am going to select the one that's the same as the laser field. Right? So all of this apparatus is there to do that one thing.
Okay.
Right? Okay. Good. So this is what the apparatus itself looks like. You have a laser, you have the second harmonic generator. You can see it's a little bit green. You have the optical parametric oscillator and also shining green from some green fields being in there. A homodyne detector, and what you can see in this picture is that right behind this whole optical table is the output port of the gravitational wave signal. And this picture is taken at the Washington Observatory. So we do this. This is what the experiment looks like. You don't have to worry about too much about it. Simply know that this is what the interferometer looked like. Here's a laser, and here are the arm cavities, etc. This is the output port right here, where the output photodiode, where we measure the gravitational wave signal. What we did was we took this squeeze vacuum source with all these details I'm going to not tell you about. We injected the squeeze state into here. What that's equivalent of is basically what I've already said before. We're putting in correlated photons into this interferometer, and here are the results. So the red curve is what we have without squeezing injection, and this was done, by the way, in initial LIGO at the time of right before it was torn down to build advanced LIGO. And this part of the curve, right up to about 150 hertz, is where it was shot noise limited. Below that, it's at other noise sources. And then when you turn on the squeezer, so where you were shot noise limited, you see the improvement. And in this case, we see an improvement of about 2 dB, which is 25%. And look at the do no harm rule. It's also kind of upheld. This is a zoom in of that, where we can see that anywhere where we had shot noise, we actually were making an improvement. I'm going to finish right about now. All right, I'll just point out that a similar measurement was made in GO600 as well, where GO600 was shot noise limit, and you can see the same kinds of results. So I'm going to stop here with one sort of conundrum and question that we'll pick up as we go forward, and that is, why only 2 dB? Remember, I've set this goal of 10 dB, factor of 3, and in fact, we're only doing 25%. So we'll pick up there in the afternoon, and we're going to walk our way through how to do better, and then we'll move on to other things. And at this point, it looks to me like I will be seeing you guys tomorrow. But I'll confirm that. If you're sick of me, we can also just do it by vote at the end of the afternoon talk. Okay, great. So let's just pick up where we left off. And Sheila, thank you for that little interlude, because now we're back to hard work. But I do have to say, there's something that I observed about just as Sheila was talking. You know, we always think of quantum mechanics as really bizarre. Actually, politics is even more bizarre. So let's get back to normalcy here. Okay, so I left off right here where I told you we did this experiment where we injected a squeezed vacuum state into initial LIGO, and we saw this improvement, and the improvement is, if you follow nothing else, it's just that the blue curve is below the red curve. So now I left you with this idea that this improvement was only 25% or 2 dB. And really, what we're trying to do is we're trying to go for a factor of 3. So what's going on? Where do we go from here? And how can we do better? So let me just spend a few minutes telling you what happens to squeeze states. And squeeze states are actually like any other quantum state. You probably have heard the words. Quantum states are very fragile. And so now here that is in action. So let's talk about the fragility of the quantum states. So what destroys this kind of quantum state? This is an optical state, and therefore what destroys is optical losses. So let's just look at this in a very simple way. You can take any mirror, whether it's tilted like this as a beam splitter or it's your incident on it at normal incidence. You can think of any mirror as having some loss, which we can write as eta. And then when some field of amplitude A is incident on this mirror, most of it gets transmitted through, but some of it might just get scattered out, and that goes as the squared, where eta is much smaller than 1 in this case. So that's the model we use. And then you can see very quickly both equations, but also very intuitively why losses are very bad for squeeze states. So imagine you have such a lossy system now. Along comes your squeeze state, and it has, most of it should travel through, but some of it got scattered out, that little bit proportional to eta. But remember, open quantum system, alert, what's coming on the other side is the vacuum, right? Open system means your vacuum state. Now you can kind of quickly see, even if you don't like equations, you can quickly see you take a narrow part of the ellipse, you add a fat part of the circle to it, and your narrow ellipse becomes fatter. Okay, it's as simple as that, and that's exactly the scaling that goes. And you can see that if eta is equal to 0, then you get your perfect squeeze state that came in back. But as eta gets larger, you start to add more and more of this ordinary vacuum state, and your squeezing gets destroyed. And that's really what's going on in our system as well. And so this is the kind of thing that we can do then. So here is a plot of how much squeezing we can generate inside of the squeezer. Now when I talk about the squeezer, the workhorse of the squeezing is that optical parametric oscillator, or OPO, the thing that takes 2 green photons and makes 2 correlated red photons. And so when we look at how much squeezing we can make as much compared to how much improvement we can get in the measurement, which is what we call measured squeezing at the interferometer, you can see that what you would really like is just to have a straight line with a slope of 1. And it's not at all that, and the reason why is that all these different curves represent different levels of loss, and the lossier your system gets, the further away you deviate from the unity slope line. Now there's another interesting thing that's also very intuitive about this plot here. you start off actually with these lines going pretty close to a slope of 1, and then as you get to more and more squeezing, you deviate away from that. And what that says is the more squeezed your squeeze state, the more quickly the losses will hit you hard. And that's also very intuitive, right? If you have a very narrow ellipse, and then you add to it some amount of loss, your fat vacuum state, your narrow ellipse becomes fat more quickly. Okay, so I mean, these are very technical terms, right? Narrow ellipses, fat states, etc. But you get the point. I want to get you some intuition for why, as you think through the future of gravitational wave detectors and these kinds of systems, these are very hard because of something very fundamental, and it's the optical losses. But anyway, if you then look at what happens here, this is where we were with the what we call the H1 or the Hanford 1 test, and this is where we want to be with advanced LIGO. So we want to get here to something like 6 dB measured. We regularly in our squeezers make 12 to 15 dB. So we're always around this band here in terms of what we generate. And so what we have to do to reach the advanced LIGO goal is we really have to move ourselves down to these to losses below 20%, optical losses. Now, where do these optical losses come from? The optical losses come from the roughly 50 optical elements that the squeeze field has to go through before it reaches the interferometer. And you can see, even if you have very good mirrors, each of them contributes just well under 1%. It adds up very quickly when you have very many of them. So that's the name of the game. And so that's one of the things we'll have to do. Now, there's another thing that also causes a lot of trouble. And someone actually asked me during the break about why don't we just make the squeezing ellipse narrower and narrower and narrower. In principle, we could, and it eventually doesn't help you. And this is the reason why. So what happens is, this is your signal field again, the red phasor. Here is your nice narrow squeeze ellipse. Now it turns out that if the angle of this ellipse fluctuates, and it does because everything in the lab environment fluctuates, then notice what happens is that you start to sample the long part of the ellipse. And remember I told you early on, that's a real no-no. And the narrower this ellipse is, the smaller, the more noise you sample for small fluctuations. Right? And so that's really the issue. And that's what's drawn on this plot here, which is that as a function of the squeeze angle, or quadrature angle fluctuations, how much squeezing do you measure versus how much you make? And same kind of thing, the narrower your ellipse, the more quickly you lose, and that's what limits it here. And so that again then takes us to, this is what we had during the Hanford 1 test. We had something on the order of, you can't tell because all these plots are piled up on each other, but it was around 40 milliradians of fluctuations, and we were generating something like 6 dB in the OPO, and we should measure 4 dB. And remember, you ask, well, you measure 2, so where 4 doesn't give 2, but that's because these effects pile up on each other, the losses plus the squeeze angle fluctuations. And this is where we want to be for advanced LIGO, which means we have to get our squeeze angle fluctuations down to about 10 milliradians or less. And we can do that. And I'll show you in a moment how. Okay, so what's the prospects for third generation gravitational wave detectors? Now, third generation is something that I'm going to be very clear about. This present generation of detectors that's coming up, with the technologies that we're using and the scale of 3 to 4 kilometers, are what we call second generation interferometers. When I talk about third generation interferometers, I'm totally talking about new facilities, really sort of radically improved sensitivities, etc. And this is only my preference. It's not what's universally used in the field. But the prospects for third generation detectors is really right here. The path to improve squeezing, so this is now what you can expect for the total losses, optical losses, and this phase noise where the squeeze ellipse is jittering around. And you notice that if we want to be at the place of actually having a factor of 2 improvement, so 6 dB is what we want to have as the measured squeezing, this is what we want the improvement to be, then we want to be up here in terms of both losses and phase noise. So we want phase noise of under 15 milliradians, and we want losses of under 20%. And now I'm going to show you the reason why I myself remain skeptical that we'll get to 20 dB of squeezing, which in many proposals, especially from our theorist friends, in theory writing a number 20 versus 10 is easy. But here's why it doesn't work. look at where you need to be for 20 dB. You need to be down here. And that says you need losses that are well under 1% total over the full optical train. And you need phase noise that's also of order milliradians. And so I remain optimistic that we can reach sort of the 10 dB level. That's going to be very, very hard. But getting down to 20, unless there's radical changes in optical technology and optical losses, it's not going to happen. Now, it turns out many quantum systems are plagued by the same thing in open ports in quantum systems, including ultra-cold atoms and those kinds of things. So we're not unique in our problem, but there isn't a solution out there.
So I'm sorry, because I'm pretty sure you said this earlier and I've just already forgotten, but when you talk about losses, is this losses in the detector as a whole, or just in the part of the instrument that handles the squeezing?
It's the latter, but remember, the detector as a whole also matters, because that squeeze field is going into the interferometer. And remember, in my thought experiment, I made those end mirrors perfectly reflective, and they're not. So there's any place where and a typical mirror, even a very good one, will have few tens of parts per million of loss. And anywhere where you can scatter a coherent photon out, you can scatter a vacuum photon in. So just think of it as a reciprocal system. That again, this is just comes straight to us from quantum mechanics, from unitarity, etc. So that's the issue. Good. All right. So that's where we're planning to be. That's where we hope to be for advanced LIGO, and I think that's achievable. Now let me finish up the squeezing discussion with frequency-dependent squeezing. Remember I told you we'd like something where we can rotate the squeezing ellipse as a function of frequency? Now, how can you do that? One way you can do that is to actually couple your squeeze field to an optical cavity. Now, I have a question for you guys. When you worked with Andreas Freiser last week, did you work with optical cavities? Yes, someone put that thumb up. The rest of you are quiet, so maybe you already forgot. So one of the things you must have learned about the optical cavities, and I'll come back to this in a little bit, is that the optical cavity has a frequency-dependent response. Now what that means is that, like any other oscillator, for an optical field inside the cavity, there's a resonance. So this is the magnitude squared of the. So you can think of this as the optical power in the cavity, as a function of the cavity length or the laser frequency. Those are interchangeable, right? So there's a Lorentzian, that's just a resonance. Now it also turns out that if you looked instead of looking at the magnitude, if you looked at the phase of what happens to an optical field inside the cavity, it also goes through a resonance right here, and it goes through a 180-degree phase shift. This is nothing magical here. This is just simple classical resonance over there. So what you can do is this phase shift, which occurs right at the cavity resonance, you can use this phase shift as a way of rotating the squeeze ellipse. Because remember, the orientation of the squeeze ellipse is simply given by the rotating vector, the phasor that you rotate. So you can rotate that to anything. So that's easy. You can say, and this idea has been around again since the early 2000s. Take a squeeze field, couple it to an optical cavity, and get the rotation you want. Now there's one important thing to know here. Why do we need rotation at all in LIGO? You need the rotation because LIGO has 4-kilometer long optical cavities in each arm. I think you must have talked about that, right? And what those 4-kilometer long cavities do is that tells us that this cavity has a pole or has a storage time, if you will, of few milliseconds. Okay, so that's the thing. It stores the light for on the order of a fraction of a millisecond or around 100 hertz. And that's really what's going on for why we need the squeezing to rotate too. Is that for light that's inside of this, stored within the time scale of the cavity, it sees a phase shift. Light that's promptly reflected back from the cavity doesn't. All right. So LIGO's cavities have a storage time or cavity pole, if you will, in the frequency space of around 100 hertz. Now, how do you make a cavity with a storage time that long? Storage time of cavities, people remember what it was? How do you get to storage time of cavities? Very simple, but let me see if people remember.
Better mirrors.
Better mirrors, but why? What's the basic principle? How do you take a light beam and store it in a cavity? Normally, if the light beam goes to the end mirror and comes back, it's just the speed of light times divided by the distance. That tells you how long the light beam will stay there. What you do in an optical cavity, of course, is that it doesn't just do this round trip. It does this many, many times. So it's done by the number of bounces in the cavity. Okay, and that's the key thing. So you can make the cavity long, and so the length of the cavity matters, and you can give it a lot of bounces, which is a quantity called the cavity finesse. Right? Those are the two things you use to adjust the storage time of the cavity. So if you go to virtually any lab in the world, and you say, I want a cavity with 100 hertz line width, you get laughed out of the room. Because most cavities in most labs are this big, and though their line width, even though they have many, many bounces, even with tens of thousands of bounces, those come out to be tens of kilohertz line widths, not 100 hertz. How do you get to 100 hertz? You go from a meter long cavity to a kilometer long cavity. So very first thing you want is, if you want the squeeze rotation, you would say, well, that's so easy. LIGO has kilometer-long cavities, just coupled to another kilometer-long cavity. And that's hard. It's really expensive. So this is data that shows that if you can get the number of bounces to be large, to make very low-loss mirrors, then you can actually create those rotations at kilohertz. And so these data, simply these colored plots, are all for showing different rotations of the squeeze ellipse. And you can see that right around a kilohertz, this data was for a kilohertz, this is the best this cavity could do. This black line is the locus of all the squeezing you can get. So you get pretty good squeezing, 4-ish dB out at above a kilohertz. Then you see this kind of bump because the system isn't perfect, it's lossy, and then you see squeezing again. With this 2 meter long cavity, we can actually do the squeezing rotation at kilohertz. To get down to 100 hertz, you need to make the cavity roughly 10 times longer. So you can do this with a 20 meter cavity. That's what we're working on now. So I want to now just wrap up the squeezing by going through the checkbox. Where are we at with our wish list? High levels of squeezing. Well, I think 6 dB measured we are confident we can get. To do that, we need high nonlinearity. We have very good nonlinear materials, and we need low optical losses. You've seen where we're at with that. That's the limiting factor. Then we want squeezing in the audio frequency band, and what that really forces us to do, because of all the jitter on the squeeze angle and backscattered light, we need to actually put the squeezer, the OPO, in vacuum on a vibration isolation system, and we're doing that.
So is this a physical jitter on the laser that's causing the...
It's a physical jitter, again, in the optical path. So it could be in the laser, but that we control pretty well at those frequencies. It's really literally to do with path length fluctuations, say in the OPO itself, for example, which itself is a cavity, or anywhere along the path if there are fluctuations, basically of the squeeze field relative to that local oscillator or signal field that we measure against. Right? So it's basically you take your signal and you take your squeeze ellipse and anything that makes relative jitter. It could be this guy or this guy. It doesn't matter. So, okay. Then long-term stable operation. For that, we need very high bandwidth control loops, which we've done. And then finally, we want to have broadband squeezing with no harm done, and that forces us to go to these tens of meter long filter cavities to get frequency-dependent squeezing. But I think if I were to go through and put a checklist on this, I would say we're in good shape for this. And in fact, we're about to install the first of these squeezers, an in-vacuum OPO squeezer, in the Livingston Observatory after Observing Run 2, which should end at the end of this month. So, and for anyone who didn't hear, if it's been discussed here before, Virgo joined the Observing Run 2 this morning. So there's also, progress there. But anyway, Observing Run 2 will go through August, and at the end of that, when in the next commissioning break, we are going to install the first of these in-vacuum squeezers in the observatory. So I think this is a technology that we are pretty confident it's going to go ahead. No filter cavities now, but that may come after 03.
So the Virgo is obviously a different instrument than LIGO, but are they implementing or planning to implement squeezing as well at some point?
Planning, but I don't think it's anywhere in the near-term list of things to do. So Virgo has a lot of, I would say, low-hanging fruit to get first. So yeah, but in principle, squeezing will help any instrument, whether it's Virgo, Geo, Kagra, just anywhere where you're limited by quantum fluctuations, which any self-respecting gravitational wave detector should be, then you should be able to use the squeezing. Now you'll hear later about LISA. And in LISA it won't help very much because it turns out LISA is limited by having too few photons. So squeezing them won't help. LISA is not a place where you're limited by the shock noise of a steady beam. All right, so this is where I wanted to reach at the last talk. So I'm about to start part 2. So any questions before we do part 2?
Just for information, the Hanover squeezer is going to Virgo. And I mean, we already, they're preparing already.
Okay.
To go on, so it may not be very long to Virgo for squeezing.
Oh, okay, good to hear.
Question. So can you trade off frequency squeeze in like low frequency, high frequency, or there's no actually trick use for that? For example, for binary systems and or black holes and so.
Yeah, so the question is, can you trade off low frequency for high frequency where you don't get broadband improvement, but say you can do the converse of the plot I showed, where you improve at low frequencies and let the high frequencies go to hell? And the answer is yes, and that is done with a very simple experimental knob. So that we can do anytime. So, good. Okay, so then let's go to part 2. And part 2 is labeled optomechanics. So now I'm going to take you on a journey of combining optics with mechanics. So until now, I've treated these two things separately. Earlier today, in the first part of my talk, I told you you keep mirrors very still, and then you use light to probe their position. And I pretended like the mirrors and the lights don't really couple. Now I'm going to break that myth and show you that the light and the mirrors couple very strongly, and you can't treat them independently. And in fact, when you treat the system correctly, as you've already seen with the radiation pressure, you've already been introduced to that idea, it's both a pain in the butt, but it's also an opportunity. So let's look at that a little bit, okay? So here's optomechanics and radiation pressure. So let me again go back to history. This is actually one of my most favorite abstracts of all time. And I'll tell you why. So look at this part. So the title of the paper is Quantum Mechanical Radiation Pressure Fluctuations in an Interferometer, and it's from July 1980. And look at this sentence. There has been a controversy whether quantum mechanical radiation pressure fluctuations disturb this measurement. This letter resolves the controversy. They do. Now, wouldn't you love to be able to write a paper with that kind of abstract? Okay, so I think it tells a very powerful story. It says that leading up to the early 1980s, there was a controversy. People didn't really know what the role of these quantum radiation pressure fluctuations were. And let me give you some sense of why. None of you have really, seem to be too disturbed by this rather shocking fact that you take electromagnetic vacuum, and you can turn that into physical motion of an object. You have this mirror that's being kicked around by vacuum fluctuations. And at the time, you seem undisturbed by it, but these folks were very disturbed by it, and certainly I was the first time I heard it. And so it's a pretty radical idea to think about. But here it is, and it's a significant limitation to the sensitivity of gravitational wave detectors. So we have to deal with it. So that's what I like. So now, when radiation pressure dominates a system, you kind of have to break it into two parts. You have to break it into classical effects and quantum effects. When you look at the classical side, it turns out radiation pressure is both a blessing and a curse. Some of the classical effects of radiation pressure are actually used to improve the sensitivity of a gravitational wave detector, and I'll say a few words about that. But it turns out that when you get into the quantum regime, you actually can also use that, even though there's the quantum radiation pressure noise, which, by the way, I will often refer to now as QRPN. It can be used to directly observe motion of objects. It can be used to actually generate squeeze states of light. Now, I want you to not be confused by this. Everything I've shown you about generating squeeze states of light right now, we've done with a nonlinear optical interaction. Remember I showed you that Hamiltonian? In a few minutes, I'm going to show you an optomechanical Hamiltonian that gives you the same thing. Okay, so that's interesting. And it turns out these systems have also been, this kind of radiation pressure coupling has also been used for preparing quantum states, and I'll show you a little bit about that. It's widely seen as a very promising path for the tool bag of quantum information science. I will say nothing about that, but if you're interested, I can say a lot more about it separately. Okay, so you can come talk to me. So just as I gave you a quantum optics primer, I'll also give you a primer on optomechanics. Now, every cavity optomechanical system that people consider is made up of something that looks like this. You have a laser that pumps an optical cavity where one mirror of the cavity is movable, and the other mirror we tend to just ignore. We just think it's infinitely heavy and just sits there compared to the movable mirror. And the name of the game in this system is going to be this kind of thing. So you have this laser field, it's an optical field that couples to a mechanical mode. Okay, so the Hamiltonian I showed you earlier was two optical modes, remember the green mode and the red mode? This is now going to be the Hamiltonian of an optical field and a mechanical mode. And this is shows up a fair bit in condensed matter systems as well. And so you'll start to see some rather, some other language show up, but I'll try to explain it as I go. So the Hamiltonian for that kind of system to first order is the cavity mode. So A is the annihilation and creation operators for the cavity field, and omega subcavity is the cavity resonant frequency. B is the mechanical mode frequency. So these are the annihilation and creation operators for the mechanical mode, which, by the way, in mesoscopic physics parlance, is sometimes called the phonon mode. Okay, so now we're talking about photons and phonons, all right? And then finally there is the coupling term, and this coupling term is just the radiation pressure term. Look at the A dagger A, that's the number operator for the optical field, so number of photons. And B plus B dagger is just the position operator for the mechanical mode. Okay, so it's pretty intuitive Hamiltonian. With one thing, by the way, G0 is simply the coupling constant. It's written in terms of the 0 point position fluctuations, and it's really a very interesting thing. What it's really telling you is that if my mirror moves by one 0 point, one quantum, it will shift the cavity frequency by this amount. So and if any of you who've studied cavity QED systems, this is very, very analogous. In cavity QED, you take an optical cavity, you put an atom in there, and then the interaction with the atomic system will pull the cavity frequency. Here, the interaction with the mechanical system pulls the cavity frequency. Okay, so if you've seen this in other contexts, and if this looks like a James Cumming Hamiltonian, it's because it is kind of, okay? And for those of you who've never seen a James Cumming Hamiltonian, it doesn't matter, forget I said that. All right, so now comes this problem is that this is not a difficult to solve nonlinear term, right? Because it's got this number operators, you have raising and lowering acting on this position operator, which has raising and lowering of the mechanical mode. So we just do a little linearization, and the linearization approximation is simply that you write the optical field as a coherent state plus some little fluctuation. And that's completely just what laser fields do. So we're allowed to do that. Then you do a Taylor expansion about the number state, and very quickly you'll start to throw away terms you don't like. So the first term you can throw away is this alpha squared term. That is nothing but a DC force on the mirror. The mirror moves back in a DC way. There's nothing fluctuating about it. We can easily push back, and in our experiments we do, so we ignore that term. And then we can also ignore this term because it's second order in small fluctuations. And now you get this simpler term that gives you the Hamiltonian that you're interested in, and this is the coupling term that you now have. And you can see very quickly that this term that this term right here looks now very much like this, the nonlinear optical interaction I'd shown you earlier, where you have a optical mode is created when a mechanical mode is destroyed, and vice versa. So this is now, you can just think of this as nothing but a scattering term that scatters phonons to photons and photons to phonons. Okay? So, and just as we had done with the earlier one. So in this system, what you now have is you can simplify it. You have this mechanical mode B, and it is described by its damping rate and its mechanical frequency, so get big gamma and mechanical frequency. And then you have this optical mode where you have sort of average out over the fast rotations of the optical field, and you see that the cavity has its own damping rate, which is the rate at which photons leak out of the cavity, and it's detuning from resonance. And you put those things together, and you can rewrite this guy in terms of these, you can think of this in terms of this very simplified system. Here is your mechanical oscillator, here is your optical oscillator, and here is the coupling constant between them. And now you have two experimental knobs to turn, which are both contained inside of G, this coupling parameter, which is the detuning of the optical cavity, of the laser field from the cavity resonance, and the number of photons. Okay? So what do? I can detune the cavity, and I can change what the power in my beam is. And those are two things that can be done very easily in experiments. And that gives us the coupling Hamiltonian for this optical coupling. So I'm going to skip this part, but I'm going to show you one really interesting thing, which you can now see the power of this technique. So let me start with a picture that isn't drawn up there, but I'll draw over here first. And that is, imagine that I have, this is the optical resonance. This is an optical cavity. And so one mirror, this is the resonance condition of this big mirror and this little mirror on a spring. Okay? Okay? Now, what happens to this optical field if this little mirror starts to move? Okay? If it moves at some frequency omega, then what happens is that the optical field here acquires a pair of sidebands at minus omega sub m and plus omega sub mechanical. Okay? And nothing special happens there in that particular case, because this sideband and this sideband have equal amplitude and opposite phase, and so the phasors of these sidebands rotate completely in phase, and they're just, you would see this as a signal in the cavity field, but nothing interesting happens. The interesting things happen in terms of scattering is when you get to detuning. So here is now a case where the top case, so here is your cavity mode, and now what you've done is you've detuned your laser field so that it's not resonant in the cavity, but imagine that the lower sideband is resonant in the cavity. Now look what happened to the two sidebands. The lower one is much enhanced by the cavity resonance. The upper one is completely suppressed. You have this big sideband imbalance, and that's equivalent of scattering a laser photon into a mechanical mode. So it's a photon to phonon scattering, but going to lower energy. Okay, and then the converse is true if you detune to the other side. So when you scatter photons into lower energy, what you're doing is you're actually you're imparting energy into the mechanical mode. See, the mechanical mode is enhanced here by energy it absorbs from the laser. On the opposite side, when you detune the other way, the laser photons have more energy, and that's essentially a cooling, because now what they're doing is they're taking energy out of the mechanical mode. And so if you've ever heard of optical cooling of atoms or optical cooling and trapping of ions, same physics. Except in the case of atoms, you're looking at the internal degree of freedom, some transition. In the case of the mechanics, you're looking at the actual average motion of the mechanical oscillator. If you were looking at some other mechanical system with phonons, you might be looking at the internal vibrational states of a system. That would be vibrational phonons. But the physics is exactly the same. If you have a cavity and you detune, such that you can scatter more or less energy into the phonons, you heat or cool the mechanics. Okay? This is slightly complex to wrap your head around, but I think the ideas should be out there. That putting this in a cavity and detuning it allows you to either heat or cool the mechanical modes. Yeah? All right. Now, there's this incredible explosion of optomechanical experiments going on all over the world. And I've put this chart here in units of mass scales, but you can do it in units of frequency, which is, so the lower the mass, the higher the resonant frequency of the mechanical system. So here are our picogram systems that resonate at gigahertzes, the mechanical resonances. All the way you can walk down this thing to these last 3 experiments. And why I point these last 3 experiments out is these are experiments that go on in our group. And why do we work on this ridiculous end of the spectrum? That's because, remember, all of our measurements in gravitational wave detectors have to happen at 100 hertz. So doing experiments at gigahertzes does not help us in understanding our gravitational wave detectors or in developing tools for them. So we work with systems whose mechanical resonant frequencies are somewhere between 1 and 100 hertz. Okay? And that's really why we are on this heavy, big end of the spectrum of all the possible things. So I told you can break these things up into 2 parts, which is the classical parts and the quantum parts. The classical parts are essentially what can we do with these forces. So another way to say the same thing is what can we do with these scattering processes that I just described, where you can either heat or cool the mechanics using an optical field. Okay? And then the quantum part is really can you access the standard quantum limit, which I had talked about earlier today. Can you produce quantum states of mirrors? Can you produce squeezed states of light? And I'm going to say a little bit about all of those things in a moment. So let's look at the classical force, not in this sideband picture, but in something that might be more intuitive to some of you. But it's really the same thing going on, but just different language. This, again, is the cavity resonance. What does this mean? This is the power in the cavity as a function of the displacement of a mirror from resonance. So it's really just exactly this peak right here. Okay, this. Okay. Now, what happens? So, of course, the radiation pressure force is proportional to the power, right? We all know. Everybody remembers that, right? From their pointing vectors. Force is proportional to P over C. Ring a bell? Okay, good. So that we know. All right. So now, imagine for a moment that you, instead of operating right here at resonance where this force is quadratic, we want to go to a place where it's linear, so we go detune ourselves to say this midpoint down the cavity resonance. And let's look at what happens when we detune ourselves to higher frequencies, what we call the blue detune side. So imagine for a moment that you're sitting right at this midpoint, and you pull your mirror outwards a little. So your cavity gets a little bit longer. What happens to the power? Your cavity got longer, power goes down. What happens to the radiation pressure force? Power went down, force goes down, mirror gets pulled back in. Whatever was pushing it out, the radiation pressure force that was pushing it down reduces, pulls back in. Does that remind you of something? I pull something and something pulls it back. Restoring force, spring, it's called an optical spring. Okay, so this side is an optical spring, and there's a little detail that's important that's not easy to represent on this picture, but because the cavity optical field doesn't respond instantaneously to the displacement of the mirror, you have an imaginary term, which is a damping term. Okay, so on this side, when you're blue detuned, you have this restoring force. Force is proportional to minus kx, Cook's law. But you have a damping term with a positive sign, which for us is actually an anti-damping term. So instead of this oscillation damping with time, it actually grows exponentially with time. Okay, so that's what an anti-damping term does. Now, on the converse is true when you red detune. When you red detune, you get a anti-restoring force, but you get a damping term, and so now you can see where we're completely equipped to do something really, really amazing. You have a damping, a restoring force. What is that? That's a quadratic potential. It's a trap. Whenever you hear about optical trapping, you've made a quadratic potential, but here we're making it for a mirror. Okay? And then on the converse, the damping term can either give you cooling or heating, depending on whether you're anti-damping or damping, because you're either suppressing the oscillations or enhancing them, growing them. So what you're seeing here in this very pictorial way is an optical trap, but for a mirror instead of for atoms or something else, or tweezers or something else. And that's something that we can use in LIGO. So this green curve is the frequency, is the sensitivity of advanced LIGO. And all of these other curves are curves you can generate by detuning the LIGO cavities to make optical springs. And so what you see here is, in fact, this is an optical spring effect in advanced LIGO. These are theoretical plots. But what you see is that in this regime here, because of this optical spring, you can see that the sensitivity actually goes better than the standard quantum limit, the black line. Remember I told you can evade it? And it does that because this optical spring is correlating your shot noise, radiation pressure noise again. So it's scattering photons from one regime to another. Okay? So that's one place where you can use it to your advantage, and of course we do. Now, in terms of why we wouldn't do that in advanced LIGO, say tomorrow, is really because it turns out that the thermal noise that we expect, remember that thermal noise I told you, the coding thermal noise? It's going to mask that whole effect. So we can't really take advantage of it, but if the thermal noise were to improve, that's where we could go with this optical spring effect. Okay? So that's one place where it does something good in LIGO. Now, and you can see, actually I won't spend too much time on this, but you can see that these are all different configurations for advanced LIGO that people have thought about that are optimized for maybe neutron stars or for specific specific pulsars, etc. That you could, in all of these cases, you're using this optical spring effect. Okay. All right. Yeah.
How quickly could we switch between these? Is it like that we just flip a switch? Essentially, the laser will be differently.
It's a lot harder than that, and that's also why we wouldn't do it right away. Even if, so if there was motivation to do, if the thermal noise was much better, there's still a lot of hurdles to cross.
Oh no, I mean switching between these different like.
Yes, you're saying can I have this plot in the afternoon and this plot in the evening?
Yeah.
Yeah, no, it's a lot harder than that. In part because when you operate these cavities detuned, a lot of other noise sources that used to couple quadratically because you were on the peak of resonance suddenly couple linearly. So you start getting other noise sources that you have to control better. So it's not a piece of cake. This is an example of where this is an effect you could use, but it would take some work to make it work. Now, the motivations for these things, actually I won't talk about motivations because you guys are all very well motivated to come here. Now let me talk a little bit about, all right, so now give me a second here. Oh, geez, this 220 volt stuff is really tricky. Okay, now, what happens, what's the flip side? Why couldn't you use these optical spring effects and just make any sensitivity you wanted and do anything you wanted in terms of making quantum states? Let me just tell you, if you pay attention to nothing else for the next 10 minutes of my talk, there's one thing you should take away, and it's thermal noise. Anytime you want to observe mechanical motion in the quantum regime, why don't we as mechanical objects demonstrate quantum behavior? What is it about us that's different than an electron or an atom or an electron in an atom? Well, you say size, and quantum mechanics says no. Quantum mechanics says I work for all sizes. Really, in the end, what stops it is that our quantum behavior is masked by our thermal motion. If we could cool ourselves down, we too could be quantum. And that's the name of the game with mirrors and atoms. You could say the same thing about atoms. When did we make Bose-Einstein condensates? You cool them down. You have to remove all the thermal motion, right? the thermal energy. So same thing is true for mechanics. And so for the next many minutes, I'm going to just tell you how horrible thermal noise is. And I hope that you will all go away after this workshop and work to solve it. But in the meantime, let me just tell you what is important about the optical spring effect. The optical spring effect is actually is really important because what you're doing is you're actually coupling your mirror to a zero temperature oscillator, if you will. The laser beam is a zero temperature oscillator. Like, I couldn't couple it to another mechanical oscillator and make this optical trap, because then the thermal noise from that the other oscillator would couple in. So that's really what I'm trying to show here. But let me say, okay, so here are the 3 scales on which we study these optomechanical systems. And so let's start with gram scale mirrors. And here are all the different people, the different generations that have worked on my group. So what are the 3? The 3 are, we work with these 100 nanogram fabricated systems, not quite similar to the MEMS systems that John spoke to you about earlier today. Then we work with these gram scale mirrors, and finally we also work with the LIGO mirrors, which range from 10 to 40 kilograms. Okay, so these are the different scales on which we are asking 2 questions. We're asking the question of, can we build an experiment in which the motion of these objects are being driven by electromagnetic vacuum fluctuations? So that's what we call the QRPN, the quantum radiation pressure noise. And then the second one is, can we use these to create interesting quantum systems in themselves? Not just to observe this quantum back action, but to also become a tool of quantum measurement. And so those are the 2 questions we asked. So here is our gram scale mirror. So here was what the experiment looks like. We have an optical cavity with a very heavy mirror, 250 kilograms, and then the end mirror is a 1 gram mirror. So this is our little movable object. And we pump this cavity with 2 colors of light. One color of light is blue detuned, and you'll recall now blue detuning makes the trap. It's the restoring force. And the second color of light is red detuned, and that makes the damping. So with this scheme, I make an optical trap for this mirror. And this is the results, this is the data. So on the left side is actually the frequency response of the optomechanical system. So what this is basically this dashed line is this is basically the amplitude and phase of the motion of the mirror in response to an external force. You can just think of it as the susceptibility. So it's really this system here is really displacement per force. And you know from really introductory mechanics that would look like this, for the amplitude would look like this, so that's the amplitude of that quantity. Here is the resonance frequency of your mechanical oscillator, and then it falls off as 1 over f squared, and that's its frequency. And similarly, you have phase, and just as with any mechanical resonance, when it goes through the resonance, you get a phase shift. Okay? So that's what this is. But now so the dash curve is what the mechanical oscillator is without any optical spring or optical damping. And then we turn on the optical spring, and as we turn on the optical spring stronger and stronger, and we can do that in 2 ways. We can just dial up the power. Remember, the optical spring comes from a radiation pressure effect, so we dial up the power in the blue detuned beam, and you can see that this mechanical resonance that used to be at just about 100 hertz moves up to all these different frequencies. And then we can also turn on the red detuned beam, and that gives us the damping and cooling, and you can see that the phase shift tells us that this is a stable trap. Okay? So you can then take that mechanical oscillator. So we have a mirror, this little 1 gram mirror. It's sitting in this 1 meter long cavity. The cavity light is detuned. Some is detuned blue to trap the mirror. Some is detuned red for the mirror to scatter phonons into photons, if you will, so to cool it. So you can then ask what's the effective temperature of the motion of this mirror. So just along the laser beam. So this is a 1-dimensional system. And that's what you can measure. This corresponds to temperatures when at the coldest of just under 1 Kelvin. So this is something you really have to think through what's going on here. So I have this mirror, and along the optic axis, it's trapped by this optical beam, such that even though the mirror is at room temperature, there's no cryogenics involved. Its effective temperature, because of how we suck so much kinetic energy out of it, that this room temperature mirror has the motion of a 1 Kelvin object. Okay? Now, if I put a thermometer on the mirror, I hope you all know it will measure room temperature, but just as you would for an atom. But if you look at the kinetic energy along the degree of motion, it would correspond to this. Now, it turns out you can say, why do you only get a Kelvin? Why don't you go colder? And the answer is we could. What we were limited by here was the frequency noise of our laser. So we actually expanded the experiment. Now you can see the two identical cavities. And in that case, now you can see these ideas come from LIGO, but same thing, we have a red detune and a blue detune beam. But now what we do is we use one cavity as a frequency reference, so the frequency noise is cancelled out by this measurement. And then we were able to reach, for this 1 gram mirror, effective temperature of under a millikelvin. Okay? So what you can see here is a technique where we are essentially cooling and trapping this gram scale object. And this, by the way, when it's down at under a millikelvin, it corresponds to 35,000 quanta. So 35,000 h bar omega. So we still have a long ways to go. We have 35,000 quanta to remove, but this is an object that's approaching, it's a macroscopic object, it's the size of an American dime that's approaching a quantum state. Now, why is this so interesting and cool? It's because there is really no other way you could do that. So let me tell you why. So in this experiment, this laser beam that makes the optical spring is 1 meter long and about 1 millimeter in diameter. Okay, and it has a stiffness of something like 10 to the 5 newtons per meter. Okay, that's the spring constant. So I can go and say, well, what else could I use that could get me something that stiff? So I could take that laser beam out and I could replace it with a rod of diamond. And I would still miss by a factor of 10. It's stiffer, 10 times stiffer than a diamond beam. Now, if I were rich enough to get this rod of diamond, it would actually do me no good because the diamond comes with its own thermal noise. And so this is a very powerful technique for taking a mechanical object, a rather macroscopic one in this case, and cooling it, laser cooling it, to start to help it approach its quantum ground state. This technique, since these experiments done in our group, has been used on nanomechanical objects, and they have reached the quantum ground state. So that, not in our labs, but in other labs for nanomechanical systems, this has been used to cool down mechanical objects to actually below their quantum ground state. Okay, so we then, I'm going to skip a lot of this, we then said, well, if we can do this in our lab with this 1 gram mirror, surely LIGO is much more sensitive. We should be able to ask the same question in LIGO. So we went to, again, this was done in initial LIGO. We did this with the 10 kilogram mirrors of initial LIGO. We went there, we introduced the detunings that would make the optical spring effect. LIGO's mirrors are 10 kilograms and they have a They have a resonant frequency of about 1 hertz. Okay? So what we did was we took this optical spring effect and coupled it so strongly to the light field that the resonant frequency moves to about 140 hertz. And then we turn on the damping field, just like I told you, and we cool it down, and the coolest we could get the LIGO system was 1.4 microkelvin, and that corresponds to about 200 quanta. So now you have to think about this. This is a 10 kilogram object. Its reduced mass is 2 kilograms, so that's a 3 kilogram. That is actually within 200 quanta of its quantum ground state. Okay? I hope I've blown your minds today, because that was the goal. Even if you remember none of the details, please be blown away. Okay? All right, so it turns out, I won't give you any sort of detailed explanation for this, but it turns out that when advanced LIGO reaches that standard quantum limit, remember I've mentioned a few times, it turns out that if you do the theory, right, it will be that benchmark will be n equal to 1 quantum. So it will be in its quantum ground state when we reach the standard quantum limit, which we should at design sensitivity. So that's another thing that's kind of amazing, which is that we are actually able to use these radiation pressure effects to start to probe fundamental quantum questions. So I asked, what distinguishes us from truly quantum mechanical systems, and someone said size. And in fact, most people will say size. And so this is now our first ability to start asking, does size matter, right? Okay, so then we also did these experiments on microgram scale, and here I'm going to go switch directions a little bit, and I'm going to tell you, we could do exactly the same experiment here. We did it on the gram, we did it on the kilogram. We could ask, can we see this, can we do optical trapping, can we see quantum radiation pressure, noise, etc. But I won't tell you about that part of this experiment. I'll tell you about something also cool and something that you're very equipped to follow now that you know about squeezing, which is that you can actually use the optomechanical coupling to make a squeeze state of light. Now, be very clear, I am not talking about making a squeezed position state of the mirror. That's much, much harder. We can go into why. But I can take this optomechanical system, and the light that I pump into it can come out squeezed. Okay? And so what's the process? The process is very much the same as I had shown earlier. You have some big mirror, which we don't care about, remember? And so let's just look at this movable mirror here. You have some light field that hits it, and when you have fluctuations in the number of photons of the light field, that causes a fluctuating radiation pressure force. The fluctuating radiation pressure force causes that mirror to move. When that mirror moves, that motion is imprinted on the phase of the light. And we have then coupled number to phase or fluctuations, of amplitude to phase fluctuations. Remember I told you that was the principle of making a squeeze state. And so that's the simple principle of doing that. Okay? And so that's now a system in which we can make squeeze states of light. And so to do that, we have and why would we want to do that? So we would want to do that because there are some advantages to optomechanical squeezing. So let me compare the 4 things you would like out of a squeezer. You would like it to be broadband at the frequencies that gravitational wave detectors care about. You would like it to be compact and scalable, and what that means is that at the moment, if you make a squeeze light source, it's about the size of this table from there till probably here, and very dense, and lots of room for both for malfunction, but also remember every optical element is an optical loss. And so we think that these nanomechanics can sort of in the way that Giles showed you earlier today with this integrated optics on a chip. These are ways in which you can make them compact, scalable, and therefore less lossy. Okay, so that's the other thing. We'd like squeezers that work at all wavelengths. If you make the kinds of squeezers I've told you about so far, which we're using these nonlinear optical crystals, you have to find materials that have good nonlinearity and have transparency at the laser wavelength that you work at. And with optomechanics, the wavelength doesn't matter. If radiation pressure force exists at all wavelengths. So that's the other thing. And then of course, you would like to be able to operate these optomechanical systems at room temperature, and that's that's something. The other squeezers I showed you, that little nonlinear crystal in the OPO, actually lives in an oven. But that's not a big deal. It's ovens are not rocket science most of the time. So those are the requirements. Crystal squeezers, which are the squeezers I've already shown you, satisfy these two pretty well, but they are neither compact or scalable, nor are they useful at all wavelengths. Whereas optomechanical squeezers kind of are in this region. They are compact and scalable. They're good at all wavelengths, but we don't yet have them operating at room temperature, and we don't know yet about their broadband frequency. So these are two competing technologies. But here is an experiment where you have these little devices on a chip. Here's the big mirror. Here's the little mirror. The whole thing is in a cryostat, and then you do the usual tricks of pumping it with light, and the light that comes out should be squeezed. And this is what we saw with this data. This data is a few years old, so let me just show you a little bit about what happens. So the simple answer is that the thermal noise is dominating the quantum radiation pressure noise. And to see squeezing, it has to be in the quantum regime. And how you can see that is there are two families of curves. The red and magenta curves are when the mechanical oscillators were at room temperature. And you can just see that the red and the purple the red is the data and the purple is the thermal noise model. And so it's pretty much thermal noise limited. And then when we cooled it down to about 20 Kelvin, you see that we are now just the black curve and the blue curve are just kind of starting to play with each other. The black curve is the quantum radiation pressure noise. The blue curve is the thermal noise. And so we in no way claim that we're seeing the quantum radiation pressure noise, but this was sort of the closest we've gotten to it. We're sort of within a factor of 2 in these systems. Now, notice something else, that these spectra are in the kilohertz range, okay? And if I showed you any such data from any of the other optomechanical systems that I showed you on that sort of roadmap of systems, those would be megahertz or higher. So we are really trying to push the frequencies down to frequencies where we can operate. So thermal noise dominated, so we immediately designed new oscillators, and we also updated the system again in the spirit of scalability, where the fixed mirror is now no longer just some big mirror, but it's actually the tip of a fiber. So you can actually take a fiber tip, you can ablate it with a CO2 laser. So you give it a pulse of CO2, the tip melts, and when it reforms in the shape of the laser beam, it's actually a very, very smooth, super polished surface. Then you coat it with an optical coating and you can make mirrors. So that gives us another direction for getting to this squeezer on a chip idea. And so we built that system, and lo and behold, again, we're limited by the thermal noise. So you can see that's the blue are the data, the green is the thermal noise, and the red is the radiation pressure noise. So when I told you that thermal noise is a terrible, wicked demon, I really mean it. And I have no experiment going on right now where we aren't limited by the thermal noise, and that's what gets in the way of the radiation of the quantum effects we want to see. So that's the work in progress again, and now we've just gotten the newest generation of chips, and here are some predictions for how much squeezing we might see with this new generation, but I don't have any data to show you. So I'm going to wrap up by telling you that these quantum radiation pressure and optomechanical squeezings have been seen in other nanomechanical systems, and I'll just give you a little feel for that. This was the first observation of quantum radiation pressure noise, and really the only thing to say is this is an optical cavity with a little mechanical membrane in the middle, and what these data show is that as you turn up the power of the laser beam, this is the thermal noise limit, and this is the radiation pressure noise, and you can see that this curve follows the radiation pressure noise. So thermal noise stays constant. As you turn up the power, you get more radiation pressure noise, and you can observe this. Notice the frequency, 1.5 megahertz. Okay, so that was and in similar vein, in another system, which was one of these picogram systems, people have also seen this teeny tiny bit of optomechanical squeezing at 30 megahertz. So I think the principles are in place. These systems should both be limited by quantum radiation pressure, and they should also give squeezing, but none of this is useful yet for gravitational wave detectors, and that's where our experiments are trying to make a difference. So let me finish by saying, look, we have this very brilliantly dark and entangled future, and I love all the play on words because we are looking into the dark and warped universe for gravitational waves. We have these beautiful instruments that are really going to give us new astrophysics and new tests of general relativity. But something you probably didn't think about or count on is that these instruments have also given us opportunities in fundamental quantum mechanics. So on the one hand, we're directly applying quantum optics in terms of squeeze states of light to make improvements to these detectors. On the other hand, just by being these exquisitely sensitive position meters, the best ever made, they are themselves very good test beds for studying quantum effects in these macroscopic effects. I'll just remind you, here is a 40 kilogram mirror that at design sensitivity of advanced LIGO, its motion will be dominated by vacuum fluctuations. It will be in its quantum ground state. Okay. So that's what I want to leave you with, that these are, that this is these are the quantum opportunities that are in these detectors. I think that's everything I have.